Yesterday's thermal conductivity instruments typically limit characterization to a narrow range of sample materials. The samples are often forced to adapt to the instrument's rigid requirements, rather than the instrument adapting to the sample and application needs. Trident, by industry leader C-Therm, represents a new paradigm in thermal conductivity measurement, delivering 3 of the most powerful transient methods in one instrument. It's better to have options. Built on C-Therm's reputation for world-class thermal conductivity instruments, Trident is dynamic and satisfies the most prominent ASTM and ISO industry standards. It combines the precision of MTPS with the flexibility of TPS and the robustness of TLS, all in one modular package. These options support a wide range of applications without sacrificing ease of use. Trident meets the needs of today's labs and is future-proof for the challenges of tomorrow. The MTPS, Modified Transient Plane Source method, employs a single-sided sensor to directly measure the thermal conductivity and effusivity of materials. The method features the highest precision and sensitivity, providing accurate test results in seconds. It offers the maximum versatility for the non-destructive testing of solids, liquids, powders, and pastes. It is adaptable for high pressure, broad temperature ranges, and environmental conditions. No regression analysis is required. MTPS is the choice method for situations where reproducibility amongst multiple users matters. With a double-sided sensor available in different sizes, the Flex TPS Transient Plane Source method provides researchers the greatest flexibility over experimental parameters, including timing and power. It is recommended for more experienced users with specialty slab, anisotropy, and thin film modules available. With no contact agent required, the hot disk-style TPS sensor is ideally suited for polymers, compacted geological samples, metals, concrete, and asphalt. Flex TPS is ideal for experienced researchers looking to push the boundaries in thermal conductivity. Sheathed in stainless steel, the TLS, Transient Line Source Needle method, offers maximum robustness in thermal conductivity testing. TLS is best suited for granular materials, polymer melts, soils, slurries, and gels. C-Therm software provides full data acquisition and analysis in one user interface, allowing full control of all 3 methods. Intuitive, logical, easy. Trident reflects C-Therm's years of experience working exclusively to provide labs, researchers, and manufacturers with the very best in thermal conductivity measurement. C-Therm's products are globally distributed in over 65 countries around the world, with full local support. Trident. It's better to have options.
Good day, folks. Welcome to our webinar. We're going to get started here shortly. I'll just do a quick audio check with John. John, can you just give me a thumbs up on the chat if everything's coming through okay? Awesome. Okay, we'll get started. Welcome again, folks, to our feature webinar presentation sponsored by C-Therm Technologies. I'm Adam Harris, CEO for C-Therm Technologies. Very pleased to welcome you today. We host these application-themed webinars highlighting different areas of material development where thermal conductivity plays a critical role in the performance of the product. What we love to do is invite our partners, our customers, different collaborators that we work with, thought leaders in the industry online to talk a little bit about why thermal conductivity is important and highlight some of the interesting novel work that they're doing that's related in some way to thermal conductivity. So we've got a great feature presentation today. We have some friends from our customer at Coolmag, Xavier Mirabet and Moses Daharo, joining us for talking a little bit about some of the work that Coolmag is doing on specially designed compounds for use as heat sinks and high temperature protection, where, of course, the thermal conductivity, the thermal management performance of the compound is very, very critically important. And so really pleased to have them join us a little bit later in this presentation and talk a little bit about some of the really cool work that Coolmag is doing. I'm also going to be joined here in a few minutes by my colleague, an application scientist here at C-Therm Technologies, a subject matter expert in method selection and characterization of thermal conductivity, Arya Hakimian, who has curated a lot of our webinar presentations over the past couple of years. He always does a great job pulling together some really interesting material from publications from some of our clients, from some of our own internal work, our own application development work, and really bringing it together in a cohesive way. So we do have quite a lot of content, I'll say, to get through today. So I'm going to start rolling into it very quickly. We should run for about an hour, and we will reserve some time at the end for a Q&A session. We're also recording today's event. So if there's anyone on your team that you can think of that would benefit from receiving this, you'll automatically receive a link to the recording, and you can share that freely. We encourage you to do that. If there's anyone you can think of that we should contact or should share this with, you can also drop that in the chat box, and we'll make a point of forwarding on the information. We've gotten a really strong response for this webinar in terms of the number of registrants. I see folks from all over the world, some from existing client sites, and some new faces too. And so if you're less familiar with who C-Therm Technologies is, let me just give you a little bit of background on our company. We're a Canadian tech company based on the east coast of Canada. Our purpose, our raison d'etre in life, is all about simplifying thermal conductivity testing for the materials of tomorrow. So whether you're formulating new composites, whether you're selecting a composite or material for a certain application in your product, you're doing validation, you want to double check some performance data on it. This is where we really thrive in producing value for our customers, is offering a much simpler, more insightful way to characterize thermal conductivity. When it comes to thermal conductivity, there are a lot of different methods. It's important to understand the distinction between the methods, and we'll talk a little bit about that as we progress through the presentation. But ultimately, our value proposition is really about simplifying your life if and where thermal conductivity becomes critically important in your product design or selection of materials. So we launched a new product called Trident on the market actually just before the pandemic started, which is a fun time to launch a product, but it's been a huge success for us. It's more than doubled the size of our group. Trident is the embodiment of a philosophy of bringing together multiple methods under one common instrument platform, because when it comes to thermal conductivity, it's much better to have options. Different materials require different approaches to characterization. There is no silver bullet where one method works for everything. If you have anisotropic or oriented materials where the heat transfer is different in different orientations, this influences the method selection. If it's a liquid or a solid, if it's a conductive material versus an insulative material, the viscosity of the material. These are all things that can influence method selection. So with Trident, we have launched the most powerful platform on the market today, where we have the benefits of the MTPS method, which will be heavily featured. That's that metal cylindrical shape sensor in front of the pyramid, which is the data acquisition system. It's MTPS. This is a patented method by C-Therm. It's very novel in offering a one-sided interfacial measurement, and you'll see it used quite heavily in some of the work that Arya talks about. It's also complemented today in work done with the Flex TPS. Flex is great for looking at anisotropy. It has an ISO standard associated with it based on the hot disk sensor. It's a great complement. It gives you more control over the power and timing parameters. So for more advanced users, it gives some more flexibility. And really, it's about having those two under one platform, where a lot of additional synergy is generated. The last one in the middle, I'm not going to probably talk a lot about today, but if you're dealing with very sticky materials, materials that bond like a polymer melt, then the needle probe is a great complement, because that's all about robustness. It's sheathed in stainless steel. It's a very, very robust sensor. And so really, it's the combination of these methods. These are the three most powerful transient methods available for thermal conductivity. And C-Therm focuses on transient methods because they're faster. They offer more versatility in where you can apply them. And something we talk a lot about in our work is championing the need to test under representative conditions. That can be moisture, temperature, pressure. In nuclear environments, it's radiated environments. It's so important to test under representative test conditions for your application. And this is very difficult to do with traditional steady state methods like heat flow meters, where it's a more rigid design. It's very difficult to introduce additional environmental factors in the testing, but these environmental factors really influence the thermal performance. So you want to be able to represent that in your method setup. So for these reasons and speed and ease of use, we really are a much bigger advocate for transient methods as we've advanced with the Trident offering. Ultimately, I love this quote from Abraham Maslow. I think it captures the value proposition for Trident really well. When all you have is a hammer, everything looks like a nail. And so the availability of different tools in our toolbox to deal with the situation in an optimal way is critically important to obtaining good thermal conductivity. The single biggest source of bad data in thermal conductivity is from taking a good method and applying it on the wrong type of sample. And so the method selection is the first and most important step in characterizing your materials. And we have a method selection guide that's available. I see John has offered that as a download link in the chat box. This is a pretty extensive guide, and it covers a broad range of methods, including methods like laser flash and other techniques. It's a great guide to help you understand where different methods are appropriate and what is the optimal technique for your given materials. Okay, maybe just a little bit of reflection on who is using the product and what is the experience with Trident. We have a page dedicated to testimonials and collecting that customer experience, but this is a nice one available from Intel. Hardeep Singh, a senior thermal engineer at Intel, just noting the Trident system allows us to not only test a relatively broader range of materials with various sensor techniques, but with the slab utility, we are able to easily test the thermal conductivity of our thin aluminum alloys, which have a high value in today's electronic and computing hardware. So nice comment there from Hardeep. He's talking about a special utility available with the Flex TPS sensor module. We have a number of utilities for the TPS, including slab thin films, if you're looking to test thin films, and we're seeing more and more of those in electronics, and also anisotropy, where quite often the orientation can be quite different. I want to end just in talking a little bit about the vision for C-Therm, and I've talked up to this point on where we've been. helping customers and where we've been very successful in producing a lot of value for customers. And that's mostly in accelerating research and development around product formulation development, quantifying that performance improvement with use of different additives as an example, material selection, incorporating into the design, validation, and all with a view that time is money, and it's our biggest enemy when we really sum up the cost of our efforts to bring product to market. Time is a big factor, and so we want to really try to compress these timelines to accelerate them where possible to get rapid feedback on product, and that's what Trident does. It's a very quick, easy way to get really representative performance data for your materials. But in terms of where we're going in the future, our vision is to really migrate this sensor technology into production environments for real-time process monitoring and control. One of the applications that's very interesting is in battery pack production, for example, where we're using a much larger volume of adhesive than we have traditionally used in the electronics industry in the past. So if you think of making like a smartphone or a tablet, here we're dispensing typically a small amount of adhesive into the product. But now with these battery packs, we're dispensing large volumes of this material. And the performance of this product in that application is heavily dependent on the distribution of the filler. The filler could be ceramic or metal or graphene, but it's there to enhance the effective thermal conductivity, and physics aren't typically on our side here. Maintaining the distribution of the filler is really important. This is an example of where you need to monitor this material as you're dispensing it, as you're applying it in the product. And so the opportunity to apply some of these sensors in situ at the point of dispensing really fits with our vision of what we're trying to do with the technology, which is, we've spent 15 years developing it in a way that really helps simplify and accelerate things in a lab environment. Now what we're trying to do is work with equipment manufacturers, with process engineers on bringing this technology into some of these production lines for real-time process monitoring, traceability on the product from a quality control point. So we're not going to talk a whole lot about that today, but if it's interesting, we have done some recent webinars on that as a topic, and we'd love to hear from you if sedimentation is a potential concern as you're introducing the product into large-scale manufacturing. Okay, at this point, I want to invite my colleague, Arya Hakimian. Arya is an application scientist here at C-Therm Technologies. I'm going to stop sharing my slide. There we go. And pass the baton on to Arya, who's going to provide a little bit more information on thermal management and EVs, talking about power electronics and chargers and different scenarios. I'll rejoin everyone for the Q&A at the end of the presentation. Arya, over to you.
Awesome. Thanks, Adam. Hello, everyone. As was mentioned, I'll kind of give us a little bit of an orientation on kind of some of these thermal management aspects in this area. Basically just teeing up a little bit of an introduction for our guest speakers, who will go into some more focused detail afterwards. So that being said, we'll jump into it. A lot of the times when we're dealing with thermal management, of course, it's related to the fact that what we want to avoid are these different component failures. Kind of a little excerpt I noted from a conference 2017. Temperature factors account for about 42% of all faults. So just shy of about half of all of these issues are coming from temperature-related components. So whether that's in an EV, in a battery, in a large-scale vehicle, smaller portable electronic devices, chargers, what have you. A lot of the times that temperature factor is a key issue that needs to be managed. So this is all, of course, typically related to thermal runaway. Just looking to give a very high-level overview here, but thermal runaway is essentially a process that is accelerated by increased temperatures, in turn releasing thermal energy that further increases the system's temperature. And of course, if there's no way to properly dissipate or let that heat escape from the system, you get this form of an uncontrolled positive feedback loop. When we're talking about electrical devices, these are typically noted to have increased current flow and power dissipation. And of course, the way we mitigate these are through the use of thermal management systems. These can take various forms, how they are constructed, the different materials, what have you. But in all cases, their main goal is to help dissipate the heat from the component or from the system in question. So today, what will be discussed primarily around these potting compounds as a thermal management system. At a very high level, again, potting compounds provide not only structural and physical support to the electronic components, but from a thermal management side, what they're doing is to alleviate some of that temperature from these electrical components. This, of course, has an improvement on the efficiency of these devices during operation, improves the lifetime expectancy, and of course, reduces breakdown and replacement requirements, which is, of course, all beneficial. And this becomes very important when groups and really the industry is looking to advance and improve things like power density in these devices, which will be touched on later in the session. But that's kind of at the core as to why these systems are needed. Kind of, again, just some background information on potting materials. There are different options out there. I kind of looked, there's three of the big ones here with respect to material type, generally being epoxy, urethane, or silicone in nature. Each one of these is, of course, applicable to different scenarios, kind of noting things like epoxies are your hardest options. They have really good mechanical strength, offering that mid to high temperature range. Urethanes are, I'd say, a little bit of a balance between the two. They have a good mechanical strength with some flexibility. Noting here that these are typically used for your lower temperature applications, and sometimes used as a cost-effective alternative compared to some of the other available options out there. And then lastly, silicone, and this one will be focused more on here today. These offer your highest level of flexibility, so really good at being able to get in and impregnate the different devices, flexible in nature, offering some of the most temperature resistance capabilities of the available options. So really great for those high temperature applications or where you're dealing with very high power output, resulting in high temperature conditions. Now, in all cases, of course, what we are focusing on is the thermal aspects, the thermal performance of these materials, which really can be tied to thermal conductivity. This may be, quite basic for some, but for those who are maybe new to the topic, want to, again, getting into thermal conductivity as a property. Essentially, what thermal conductivity is, it describes a material's ability to conduct heat. It is an intrinsic material property, which means it's independent of the size or the shape of the sample. And for us, typically working in standard SI units, thermal conductivity will be described in units of watts per meter Kelvin. Now, when we're talking about these materials mentioned, typically polymeric in nature, at a very basic level, when we're talking about how heat transfers within a polymer, this can I'd say, readily be related to the organization or the crystalline structure of these polymers. So as you get more and more organized systems, what this does is it increases or improves the mean free path for phonon transfer, which is the primary mechanism for heat transfer in these materials. So one way that you can tailor the performance of your system is by working with simply the base matrix that you're working with. So the base material, I should say, that polymer sample. Here, just kind of noting some thermal conductivities of common polymers out there. Overall, what you can see is, nothing, I would say, crazy high here. These are kind of some basic standard polymers, kind of in the range of 0.1, kind of going up towards 1 watt per meter Kelvin, but quite I'd say most often below that upper mark. And of course, again, related to different materials, different organizational structures of these samples, this can have an influence on the thermal performance. But where, again, a lot of groups are focusing on is the use of fillers in their system. So these conductive fillers providing improved heat transfer efficiencies within the sample. So this can be related to a few different aspects of the filler, whether it's simply just the loading, so how much filler you're just pumping into the system, the organization and distribution of that filler within the system itself also becomes very important. And there's also been studies simply even looking at the aspect ratio. So even if it's the same exact material, different structures, different forms of that filler can have an influence, some being better than others with respect to the overall heat transfer efficiencies. Now, this kind of brings us to the point of thermal conductivity test methods. And of course, Adam gave us the intro at the beginning where we focus on transient methods. So those would be the methods on the right there. But when we're talking about methods in general, you can really cover into 2 main classes. So transient is the ones that we'll focus on here today, but there are also steady state methods. Steady state, these are more traditional in nature. These are things like your heat flow meter, guarded hot plates, which of course have their advantages in some cases, but typically what we'll focus on here today and really demonstrate the benefit of transient options in this space, especially for these material types. And of course, this is all related to our flagship system, Trident. Adam gave, again, some background context to this at the beginning. But again, really the idea here of having 3 different methods, so different options available to you, depending on the types of samples that you're looking to test. So I'll give kind of some, I'd say an introduction to some of these methods, which will, again, queue up some of the content that will be discussed later in the session here today. And again, primarily on focus will be the MTPS and TPS methods. So mentioned the different options that are available. So why transient? Again, these are some points that really we've seen many groups gravitate towards these options for some of these reasons. One of the biggest ones is representative test conditions. Again, so this is whether you're looking to test under varying temperatures, pressurization, gas environments, humidity. These are all things that these sensor techniques really lend themselves quite well to being able to be set up inside of these different environments, which can be somewhat challenging with other techniques, again, depending on the instrument or the technique, the method that is being looked at. When we're comparing transient to steady state, another one of the, I'd say, really biggest factors when we're, again, talking about the time and cost savings related to just simply how long things can take, is transient options will always be faster than steady state. This is just simply related to inherently how the measurements work. Effectively, a transient measurement is taking a measurement of the heat change in the system as a function of time before steady state is reached. So just inherently to how this works, a steady state method will always be slower than that of a transient counterpart. And then lastly, they offer a greater flexibility on sample size. So whether it's the format of the sample, the type of materials, so solid, liquid, powder, again, typically much more flexible in nature there. So I'll start with a little bit of information on the MTPS, the modified transient plane source. This is a single-sided test method. When we're talking about the MTPS with respect to the other options available on Trident, it will be one of the fastest methods. So typically your test times are about 1 to 3 seconds in duration. So if you are, if speed of measurement is kind of your number one priority, then the MTPS has some really nice benefits there. It is also amongst one of the more versatile. So again, kind of talking about the different sample types and conditions there, very flexible in how it can be set up and what samples it can actually test. Just to give you a little bit of information on the principles of operation. Again, this is very high level And of course, if you did want to learn more, we have a range of resources available. But the idea of how the sensor works is essentially on the top side of the sensor, so in the image on the left there, there's a spiral heating element integrated into the top side of the chip. This is what's used to deliver the thermal pulse for your measurement. Now, as the measurement is initiated, what you'll see is something similar to the image on the right. You'll be recording the change in temperature that occurs as a function of time based on the delivery of that heat pulse from the measurement. And of course, different materials will respond differently to that temperature change. So things more insulative like a foam will be quite different in response compared to something more conductive like a metal. But the nice thing with the MTPS is that all of the data that is collected here, even the setting up of the measurement, the test parameters, this is all handled automatically by the software based on the calibration that is selected. So with the MTPS, it is a factory calibrated technique. So one of the benefits there is that it takes a lot of the guesswork out of the setup and the analysis. This is all handled automatically for you by the software. One last thing I'll point out with the MTPS, see it's related to the second point there, highlighting the guard ring. The guard ring, we can see that in the first image on the left there as well. Essentially, it goes around the outer area, so around the contour of the sensor itself. And effectively what it does, it helps to support a one-dimensional heat transfer into your sample. So by doing so, it prevents that lateral heat loss from occurring. And effectively what you're getting out at the end of the day is a directionally dependent measurement with the MTPS. So I'll just go over one little case highlight here with the MTPS. It's related to thermal mapping. And this is kind of, again, taking a look at that filler distribution and basically having a way to verify that. And in this example, we're looking at cured solid samples. But the idea here is if you have a material, and kind of seeing the sample on the right, this was an epoxy resin that we cured with a conductive metal nanoparticle distributed within the sample. And as we can see, is visibly non-uniform in that distribution. That's, this is by no means what we would describe as an ideal material, but what we'll really highlight here, and the goal of what we're looking to show, is correlating the measured conductivity value to the filler concentration at these different locations. So what we did was measurements were performed at different places across the surface of the sample. So we can kind of see a little test profile here. So basically the sample, the sensor, again, it's a single-sided method, which again really is why we are able to do this type of measurement. So you can take that sensor, move it across the surface of the sample, and take these discrete measurements. And what we can do is at the end of that, essentially map out the thermal conductivity value. And what we showed in this sample, of course, as we would expect, are some rather large differences at the different test locations. But this is really correlating to the filler at those individual spots. So the top left corner there, coming in about 0.347 watts per meter Kelvin, very low compared to some of the other locations. But at that spot, as we can see, there's very little filler present. It's almost closer to that of the neat polymer. Now, if you compare that to the top right corner, we can see, of course, much more densely populated with that filler, and the conductivity results coming in almost 3 times higher. So effectively here, what the sensor can do is give you an understanding of, are you getting very uniform spreading, very consistent results across the surface of material, or are we getting something like we're showing here in this case, which are very large differences, which is, of course, what we want to avoid, as these can result in hot spot buildups, just poor performance at the end of the day with the sample in question. And again, with this material, as I mentioned, very visibly detectable. But in the case where your sample may be opaque in nature, or you're not visibly able to detect those issues, well, then the MTPS can come in and really do that type of checking for you. So I'll pivot here into the TPS, and this is going to be the method that will be, I'd say, more focused in the following portion of our webinar here today. So the Flex TPS, it is a double-sided sensor, so a little bit different, of course, in construction and design than the MTPS. One of the benefits I'll highlight with the TPS is it does not require a contact agent. Some materials with the MTPS may require the use of a contact agent between the sample and the sensor. This isn't required for all samples, but in some cases it is needed. And certain materials, whether they be hygroscopic in nature, just simply react or absorb with these different contact agents, the TPS benefits from just completely removing that from the equation. So these are done to handle contact resistance. And anytime you have a contact-based measurement for thermal conductivity, contact resistance, it plays a role. And we have to have a way of overcoming that. And with the TPS, it is handled a little bit differently. One of the benefits is no contact agent is needed. There's also those specialty utilities available for TPS, which I'll describe a little bit. So there's slab, anisotropy, and thin film utilities available. The TPS inherently is a little bit more of an advanced method to operate from a user perspective, just I would say complexity-wise. There's a few more things that need to be taken into account during the setup and then also during the data analysis. But of course, one of the main benefits of the TPS is conforming to the ISO standard. So some of the folks that just you're looking to conform to a specific method standard, ISO 22007-2 is what the TPS will conform to. So from a principles of operation standpoint here with TPS, again, just to kind of run you through how this essentially works. The sensor itself is placed in between two samples because, again, it's a double-sided sensor. So you have one sample on the top, one sample on the bottom. Now, with the parameter setup, so basically, the time and the power that are used for the measurement, unlike the MTPS, which is, again, fully calibrated, the TPS, it really opens up these settings to you as the user. So you have full control over your test setup there. You have also access to some different sensor sizes. So inherently, there's a little bit more flexibility on your overall design of your experiment. At the end of the day, once you've settled on your conditions, you start running the measurement. What you'll collect is quite similar to these, really all the transient techniques, in that we're monitoring that change in temperature that occurs as a function of time. But with the TPS, there is this added step at the end once the data is collected. This is where you'll have to go through a little bit of a verification process. So because you have full control over your test parameters, you have to have a way of essentially making sure the settings that you're using are correct based on the samples in question. And effectively, there is a guidance provided in the ISO standard. There's about 6 or 7 checks that you need to run through, basically each time verifying that the settings that you use are correct and the region of analysis. So there's a manual data analysis component that needs to be taken care of as well there. Now, with the TPS, again, there's these different utilities in which you can operate the sensor. So the bulk utility is really your most simplistic form of TPS testing. It's geared towards isotropic samples. But just to give you an idea on your size requirements here, you can see the diameter of your test material will scale 2.5x the diameter of the sensor that is chosen, with a thickness of your sample scaling 1x the thickness or the diameter of the sensor, I should say. So there's a 6, 13, and 30 millimeter size option available on Trident. And with that kind of understanding, the larger the sensor, the larger the sample that is needed. Now, where many groups will gravitate towards the TPS is for some of these more advanced utilities. Again, really kind of just running through these at a high level here. The slab utility is a great option for testing thinner, higher conductivity, call them sheets or slabs of material that may otherwise not fit the bulk size requirements. Each one of these advanced utilities carries a little bit of a different setup requirement or some different inputs compared to the base functionality, but they open up some different benefits depending on the samples in question. The anisotropic utility, of course, straight in the name, it provides with a measurement of both the in and through plane direction within a material. And then lastly, the thin films utility, if that's of interest, really geared towards freestanding polymer films down into the micron range. So if you have very, very thin samples, then of course the TPS thin films utility may be a good option there. But that was just hopefully giving everyone here just a little bit of background on the MTPS and TPS methods. At this point, I'll transition to our guest speakers, Javier and Moses, to continue on with the content that they've prepared. So I'll stop sharing here, guys, and I'll let you take over.
Okay, thank you so much, guys. It's always a pleasure to be here. I mean, you've been, I think, in fact, you've been supporting us since the very beginning, since Coolmag was born. So we really appreciate it, and thank you so much. I'm still learning in every presentation that you make. So I will share my slides. Okay. All right. We'll try to make an easy and quick presentation about what we do, who we are, how and why we moved from mechanical, because we came from a chemical industry. We moved to electronics. So we will try to make it easy. And after that, if you have any questions or whatever you have the Q&A, so you have a chat. Okay, so let's start. I think before going through what we do and the products that we offer, it could be interesting to have a look into some specific topics that we really think that they are crucial to understand, or at least for us, because as I said, we came from the chemical thing. So in the very beginning, we did kind of marketing thing. We try to learn from the electronics industry, and not only the EV industry, but all the power electronics, to understand the market needs and what are you looking for, all these things. And we found interesting topics that I would like to speak in a few words. First of all, it's power density. So it's quite simple. Everyone is trying to increase power density. Every industry that we focus on has to, in fact, they are looking to decrease the size of the things, of the devices, and to increase the power. And that means, most of the cases, that means temperature. So temperature is still a bottleneck for the whole industry. And it's something that in the very beginning we noticed, and for us it's okay. So temperature is a problem. We should have a solution for it. Okay. The second thing is that when we have a look into your devices, I'm talking about choke or a charger, EV charger, whatever it is, we found three interesting topics. First of all, it's talking about materials. So most of the materials used in electronics are non-thermally conductive ones. So I'm talking about plastics, I'm talking about epoxies and polyurethanes, or even the PCB. So most of them are non-thermally conductive materials. So they're not contributing at all to the thermal management of the final device. The second thing that we found is that there is a lot of empty space. So air inside your electronics, a lot. So there's a huge volume that we are not taking profit of. So a lot of holes inside your electronics, and that's not contributing at all, because it's not empty. In fact, it's full of air, and air is a great thermal insulator. So its thermal conductivity is almost zero. So this is something crucial for the final performance. And the third thing that we found is that most, maybe the situation is changing, but most of the times the cooling methods that you're using are on a plane, so on 2 dimensions. We talk about cool plates, liquid refrigeration, and all the stuff. So there's a huge volume that, like I said, we're not taking profit. So this, for us, there were some funny things after investigation, and for sure I'm going to go through this. But temperature has a big impact on reliability and life of the final devices. There's some rule that every 10 degrees it's affecting, on a bad way, to the final performance. Okay, so this is what we found after all this first contact with your industry. We found that there is a lot of air and plastics within the power electronics. Most of the time, we're trying to protect from the heat instead of moving it. So instead of taking the heat out of the device from the hot spot to the cold spot, that's crucial. We're talking about thermal conductivity most of the times, but no one talking about the thermal diffusivity. That it's something that we found in the very beginning, in the early days when we try to understand everything. So thermal diffusivity, it's I'm gonna out through technically through this, but it's more related to, let me say, to fastness. So to how fast your material is able to move heat from the hot spot to cold spot, and it's also crucial. So to the final performance. So it's not only good to have a good thermal conductivity value, but also to have a very high thermal diffusivity, and it's related to, let me say, to the chemical thing. So it's related to specific heat and density. Okay, 3D, so 3 dimensions, and we're not cooling down power electronics in a whole volume. We're just cooling on a plane, so in 2 dimensions. And this is one specific topic that it's related to the batteries. Most of them, because it's changing also, most of them battery packs are not well designed in terms of there is a lot of empty space inside between the cells. Okay, so Once upon a time, okay, this is how everything started. Like I said, it was like 3 or 4 years ago. We've been dealing with chemicals for the last 25 years, resins, fillers, all the things. And one day we got a challenge. We got a challenge from Power Electronics customer. Okay, these guys, they have a serious problem with the choke. That's the thing. So the temperature was up to 180 degrees, was really high. So they've been testing different chemistries like epoxies and PUs. And because of the temperature, the furnaces were broken because the materials were so rigid at the moment. So the final temperature was really, really high. And the aim was to decrease the size of the choke and improve the thermal management. So that was the challenge. Okay, guys, you know about these things. Try to find something to help me in the thermal management. Okay, but we got some requirements that, in fact, all these requirements are still working today. So every time that we launch a new product, because we have a few, I mean, we are only 3 years old, but we have a few portfolio. Every time that we launch a product, we try to keep these requirements working. So it's something we can change, because we will talk about this topic later. But we can do a lot of tailor-made solutions. But at the end, we try to fill all the things. So the first thing is that we're always looking for the highest thermal conductivity value and thermal diffusivity values. Depends on the final application. Sometimes it's not necessary to have 3 bats, and it's okay with 1 bat, something like that. But we're always trying to increase it, keeping the electrical properties okay. I mean, okay, electrically isolation. So we're talking about the electric strength around between 10 to 15 kilovolts millimeter. This is a standard value for us. And it's a tricky thing, because there are a lot of fillers on the market with very, very high thermal conductivity values, but with very good electrical properties. So we have to find a balance between the electrical properties and the thermal ones. Okay, the material had to be soft, and this is a spoiler. So we choose silicones, and we choose silicones because they are soft. And why? Because they're soft. 2 different things. First of all, an easy one. They protect from the mechanical point of view. So, especially talking about the electric vehicle industry, so there is a lot of vibrations and mechanical stress. So the only way to protect electronic is to encapsulate them in a soft thing, so like silicon, for example. And the other one, it's crucial also, was there are different phenomena, but one of them is the magnetostriction. So, and just to summarize, because of the temperature, each material that is suffering stress or thermal stress, it's modifying the volume, so it's increasing the volume. And if you encapsulate this kind of things with rigid systems or rigid polymers like epoxies, for example, the temperature, the effect that you get, it's the opposite. So the temperature goes up, and you're probably gonna reach the Curie temperature, and fluids are gonna break. So and this is what, I mean, we tested a lot of things, different chemistries, and we finally choose silicones because of that. For sure, everything has to fill with UL 94V0 compliance. So every time that we launch a new thing, a new product has to fill with it, and has to be non-hazardous. So in fact, you can touch it even. You cannot eat it because maybe it's not testing very well. But there are no VOCs, no chemical things, no organic components. So there are no gas, nothing. So nothing happens once we mix. There's only a chemical reaction, and they cure it. So, but in terms of manipulation, labeling, and all the things, there's not a problem. So it was crucial also because volumes back then were not so high, but right now it's crazy. So if we talk about the LVCs, for example, or battery packs industry, the volumes are huge, are crazy. So if you've got some VOCs or volatiles within your chemicals, it's not very good. Okay. So, and finally, we made it. So we tried a lot. We tested different things, different materials, and we launched back in 3 years ago. We launched Coolmag 29. It was the very first product that right now is changing a little bit. So we were able to decrease the temperature in this scenario, in this case, like 80 degrees. It was crazy. It was very, very good because of different things. So first of all, there was no air within and inside the choke, no thermal stress because of the silicone. The dissipation was in 3 dimensions, and the fast thermodynamics. So our Coolmag will have a very good thermal diffusivity values. and why the final performance or the final temperature. Because finally, when we talk about temperature or thermal management, you think about temperature. So what would be my equilibrium temperature once my choke, or once my OBC, once my overcharger is going to be or working on a working conditions? Okay, and this is not only related to the, let me say, thermal compound performance, because this is what we found. There are three different key things to get the best thermal performance or stabilization or lowest stabilization temperature. First of all, it's the thermal diffusivity and conductivity value. That's for sure. I mean, the higher the better. Okay. Second one, it's like I said, the potting nature. So sometimes just changing same conditions, even with lower thermal conductivity value, but same thing. You change and you put soft thing like a silicone, and your final temperature drops down a lot. So I mean, 30, 40, 50 degrees. So it's crazy. And the third thing, it's very, very important. It's funny because I think that Adam in the previous presentation said that depending on you can have a good method but a bad application, but it's exactly the same for us. So this is what we found, that you can have the best thermal compound, a good Coolmag 29 LV, for example, that's our standard. There is a silicone, everything's okay, but you apply it on the wrong way. So you don't make it right. There are bubbles, there are empty space, there's something. It's not going to perform. So, and in fact, the final performance can be very, very bad. So, this is only because of the application. So I think it's good to have a look in each application, each case, and we can support with it. We will go through this later. My colleague Moises will explain about this. We'll talk about this topic, but we can help them. So we're not only providing potting resins, but also some supporting. Okay. And this is Coolmag. So I think Moises, my colleague, is going to go through this part of the presentation after all this first technical thing. Moises, I think your mic is not working. Your microphone, not yet. Don't think so. Let me check. Not yet. I think, well, maybe in the chat you can confirm if you can hear it, because I'm not hearing nothing at the moment.
No, we don't have the audio.
Oh, okay.
Yeah. Moses, just check on the upper right. There's a toggle on the start video and also the mute for the microphone. There's a little arrow down that can help you select the microphone.
Yeah, exactly.
You had a headset on earlier too. I'm wondering if maybe it was set to the mic on the headset.
Let's check. No. Not really. Well, don't worry. I can do it. Okay, Moises, we'll try to fix it. All right. Okay, don't worry. Okay, I will go through this. So after all this investigation, after this first product launch, we found that we got something interesting. We got something that is working very well. So we decided to create a company, in fact. So we're part of a group. So sometimes we say that we are kind of startup. In fact, we are kind of spin-off. So we came from a chemical distribution business, and right now we're also in the chemical manufacturing. We're part of the PMO group. More than 25 years dealing with chemicals here in Barcelona area in Spain. So we have everything here at the moment. So R&D and manufacturing, it's here in Barcelona area. Probably we will have to move to other countries because of logistics, let me say. But this is what we are. In terms of total revenue of the group, it's 31. Probably it's going to be 40 this year. So we have different customers around the world, different partners, and a lot of countries. So finally, that's what we decided. So we decided to create the company, to create an instructor. I moved from Cavian, from PMO Group to Coolmag. We bought a factory here very close to Barcelona. We're gonna have a new one probably next year, at the end of the year. And so in the industry where we are, I mean, we are everywhere. So in terms of I go through the products. So in terms of wherever is a thermal problem, we can help. So we're not talking only about the electric vehicle industry, the EV industry. but also two wheels, power electronics, so in general, tier 1, tier 2, industry, so consumer electronics, all of that. Okay, these are our Coolmag solutions at the moment because the family is growing almost every week. So I think in fact, Coolmag 29 SA30 and Coolmag Plus are quite new products a couple of weeks ago. So we are focused on silicons at the moment. So we go from 1 batt to 3 batts. Coolmag SA10 is 1 batt product. Coolmag SA30 is 3 batts, and we are trying to increase it without compromising the other properties. We got also I think probably there it's easy for you. We have also a PU resin. We don't like to use too much because we are not experts, and these are different chemistry, different world. But we have some formulations because some of the customers are looking for an adhesive properties, or are looking for an adhesive, in fact. So we can add some fillers and to get to relatively high thermal conductivity. Because I mean, sometimes you need some this addition properties, but we are focused on silicones based. They are all 2K, so you mix one by one. You can use room temperature curing, or you can increase the temperature. You can go to 40, 50, 60, 100 degrees, and the final curing time will be decreased. And the Coolmag Plus range is a different family. We can talk a few words about this. If you remember our second slide, we found that there's a lot of plastic in the electronic industry. So we decided to get the same technology from Coolmag, from silicon range, to plastics. And we launched a thermoplastic to increase all these thermal properties. In terms of applications or market, so it goes everywhere. The main market for us is power electronics, mainly for EV. I think there is a video right there. I would like to share one video because this is quite new. Because one of the questions that we really have every time that we talk about Coolmag, it's viscosity. So everyone is talking about, is complaining about this silicon viscosity. So we decided to do some videos in order to check how it flows, how everything goes. No? And I would like to share this first video. I hope it's clear.
Power electronics transformers and chokes for onboard chargers OBC in electrical vehicles are required to perform very high power management for very short periods of time with very high power densities.
All this you can use even to find the device. You can apply Coolmag on the final device, OBC or whatever it is. So it's very easy. You can use
what we need: increase efficiency, power, thermal management, and reliability.
Or even gravity or casting. So there are different methods to
reduce total losses, volume, and
like
cost.
I say, we can support you. We can give you some advice because we have a very good background.
Our solution is Coolmag 29 LV.
It's good just to have a look.
Low viscosity for flowability, thermal conductivity to remove heat, low stress, and mechanical.
But it's always good to have a look into it, and for sure you want to test it. We'll talk about this later, but you can try. And then if you go to the second part of the presentation, okay, power electronics, like I say, it's number one for us, so it works very well. Temperature can drop down easily to 30, 50, even 80 degrees, so it works very well. Also, battery protection. This is something not quite new, but we found that it works extremely well in talking about battery protections. You can use it as a gap filler because it works. So we can go, in terms of viscosity, we can go from 10,000 CPS or even lower with Coolmag SA10, but we can go to 2,000, 3,000 in talking about Coolmag SA10. We can increase the viscosity to 100,000, something like that. So you can use it even as a gap filler. And in terms of battery protection, Coolmag works very well as a gap filler and even as a potting resin. So this is something interesting. I will go through this because I think that it's very funny. So it's quite new. This is the new Tesla battery pack. And as you can see, if you go to the Monroe YouTube channel, I really highly recommend you to have a look into this, guys. Tesla changed completely the strategy. So right now they're injecting the whole battery pack with a potting resin because it protects from the thermal runaway in a very good way. It also protects from the thermal point of view, so less charging times and higher, high efficiency. and also protects from very low temperatures, because you can use some heaters, and because there is no air between the cells, like in the old times, like in the picture on your left, there's a lot of air between the cells. So if you're using a potting resin for the whole battery pack, you don't have it. So you can use heating systems in a very efficient way. And after that, onboard and offboard chargers, especially OBCs, are, let me say, number one, number two for us. So it works extremely well. It's very, very easy to use. You can use it by casting, or you can inject it, or you can we can help you, because we have a huge background on that. And sometimes customers have been able to double the power density. So it's very, very, very impressive. It works very, very good. And also our Coolmag 29 LV, it's outgassing, so NASA certificated. So it has a NASA certification for the outgassing, and it's not very common for silicon. So there's no gas, especially in things like, obviously that it's completely sealed. You cannot use convection, so it works extremely, extremely well. And then inductive charging is also quite new, and it's performing. In fact, inductive charging, that probably is going to be the future in terms of charging vehicles. And I mean, it's the same problem. You have a coil, a bobbin, and it gets really, really hot. So what we do is we can do both. You can inject Coolmag, or you can just pour it over the copper coil, and it performs very, very, very well. We have a few customers making this kind of applications. And this is Coolmag Plus, like I said, this is a different thing. So it's a pellet. So you need to inject it. So it goes for, I mean, some of the big customers are making their own injection, but most of them, they're using some kind of transformer or injectors. So this is how it works. And it's there in terms of thermal properties, we're talking about 3 watts metal caving. So it's relatively high. And it can, I mean, you can do whatever you want. You can do battery packs. You can do coil bobbins. You can do whatever you want. It's a polyamide at the moment. We choose polyamide because one customer, I mean, the first certification that we have is for polyamide polymer, but probably we will try to find different chemistries. Okay, and this is the last part of the presentation, the Coolmag as a service. Like I said, we're not only making or selling potting resins, because we found that there's not too much, let me say, potting culture, especially for the electric vehicle. So the customers are not feeling comfortable with chemicals, and especially with potting resins. And like I said, the application makes the difference. So the way you apply the final product can make the difference. So we decided to create the Coolmag as a service. That it's quite simple. So we're not only providing you the potting material, but also we can do some prototyping for you, the first injection or applications. So we got battery packs, we got OBCs, chokes, traffic, whatever it is. We can sign an NDA if it's necessary. And we do the first application, the first injection for free. We put some thermocouples, and we send back to the customer to test. And once it's approved, you can do your own. You can use the same potting machines, whatever you want, or we can also help you in terms of how to industrialize, because that makes a difference. So we're not talking about making a few things per week. We're talking about thousands units. So it's very, very crucial to find the right way to make it. And that's it. I think we have also a video just to have a look into it and to check how we do it. And this is going to be the last video of my presentation. So this is going to be the outro. Check. There we go. I hope it's okay. There we go. Okay, so you're not into Spanish, something you find that you are in a hard best results. How it's working? Yes.
Okay, great.
That's
Well,
it.
thank you very much, Javier. I'll just have a few slides just to conclude on, and we'll have you rejoin us for the Q&A session here in just a couple of minutes.
Thanks.
So I'll just bring up the next. Really, just a couple of housekeeping bookends here on the presentation. So we hope you found it interesting. Do stay on the line if you'd like to join for the Q&A session. We do have a pretty extensive tech library available on our website, C-Therm.com. All of our webinars are archived and recorded there, so you can see some great ones, including some previous ones that we've done with Coolmag. So if you'd like to just learn a little bit more, the tech library and website are great places to start. A couple of events that are coming up where you can find us. We have a very global audience, and so we're really covering both sides here of the globe. We're going to be in Vietnam here in April, Analytica, and then we're also going to be at the Thermal Management Expo in the US in Novi, Michigan, May 1st to 3rd. So if you're planning on attending either of those events, please let us know in the chat box. We'd love to connect. Maybe schedule a meetup, a coffee. Could be just a very casual conversation, or if you're interested in a demo, it's possible for us even to schedule something hands-on at those events. So just a heads up of where you'll find us in the next couple of months. Our next webinar is April 18th, and it'll be on the evaluation of different battery materials of construction for batteries as profiled by DSC, STA, and TMA. This is going to be in collaboration with our partners at Rigaku from Japan. We represent them in the US. They've got a very impressive product line for a thermal analysis. One of the things I love about Rigaku's DSC isn't just as one little quick example, is they've got an optic system which can record the sample visually as it undergoes different reactions. So if there's an off-gassing, a combustion, a phase change, it really helps understand the story of your materials and being able to visually observe it and connect that to the thermogram in terms of how the changes are being reported. If you're looking to just stay in touch, follow us on LinkedIn. It's an easy way. That's our central point of distribution of any new information, any events. We also will share things that our partners like Coolmag are doing, just trying to really curate a community of folks interested in areas of thermal conductivity or thermal management, thermal performance. If you're sitting there wondering about what a potential next step might be, if you're interested in thermal conductivity, perhaps bringing the capabilities in-house to your organization, a couple of suggested next steps would be either to request a virtual demo. We do these regularly. They're hosted by ARIA. Great opportunity to see what the instrument looks like performing real measurements. We have a library of materials set up, so we have a lot of different representative samples we can pull from and demonstrate for you on different thermal greases, different compounds, all kinds of different materials. If you'd like to see what that looks like, we can schedule one of those. I think there's a link in the chat box to where you can book that. Also, if you just need a quick quote, just looking at budgetary, it is that time of year where we're revising our plans, looking at CapEx, things like that. Certainly happy to get a quick quote to you. So at this point, I want to thank our presenters, Javier, Moses, and Aria. An excellent job curating today's discussion. We covered a lot of ground in looking at different thermal compounds and heat management and power electronics. Batteries, this has huge implications for EVs, of course, which is a very hot area. And to our audience, thank you very much. I realize we're running a little bit late here. We will move to a Q&A session, but let me just say thank you again for joining us. I'll stop the recording at this point. I'll invite our presenters back on camera, and we'll proceed to the Q&A session. If you drop off here, have a wonderful afternoon, folks, and thank you again.